Hi, I'm Nigel Griffiths. I work in the Advanced Technology Centre in the UK, which is part of IBM Europe. In this technical hands-on movie, we're going to look at memory protection keys. To get access to this, you need a Power 6 base machine running a recent level of ARX 5.3 or ARX 6. It's an old programming problem when code has stray pointers that is causing corruption of memory. It's even worse because when you corrupt it, it may actually continue running for many hours, days or months before it actually goes wrong and makes it very difficult to actually track down. Now kernel programmers like this feature. They tend to call it storage keys because they see memory as a slow storage device. But even there, when they switched this new feature on, they actually found some third-party device drivers actually making mistakes inside the ARX kernel, and having identified those, they have now been eliminated. But the same feature can be used with user programs. One thing to note there, this is not a security feature. It is a feature for tracking down mutually cooperating programs and finding out where they're going wrong. And this should lead to higher reliability. A modern machine has billions of pages, and these locks and checks have to be formed very, very quickly, far faster than we can actually access memory. So we actually have a low number of locks, and any one of those locks can be associated with a particular memory page. By default, the lock is the public lock, and memory just works as normal. But a program can change the lock assigned to a particular page of memory. To do this, they use this ukeyProtect system call. You give it the address, and that must be page aligned, then the size, and it must be a multiple of the page size, and of course ARX now has 4 different page sizes, so we have to be aware of that. So now we have the memory locked, we have to work out how to get a key to access it. Well, we have a new data type called a user key set here, and we define 3 of them. We have to initialize them before we actually use them, and then we're going to initialize our reader key and our writer key, as you can see here with the user key add key. And the read key we're going to give read access to, and the writer key we give read write access to it. Once we have our keys, we decide which we've got in our hand. This is what's called the user key set activate. And so that says at the moment we have the writer key in our hand, and now we can read and write those locked memory pages. Now if we want to call a piece of code that we don't want to give it the full read write access, this is what we do. Instead we're going to here activate the reader key. Then we can call that function, and if it tries to write access to the locked piece of memory, we'll get a signal generated as sigsegv. And the same on the second example here. If we want to call a piece of code that has no access to a protected memory, then again we can call it with a key called none that we initialized earlier, and then if it does a read or a write access to this memory, we'll get the signal generated. Well, let's have a look at a small worked example. I have 2 versions of a program here. The simpler one is mem3, so we'll have a look at that now. We have a standard set of header files at the top here. There's an extra one here for these user key access. 2 macros here that just make the code a little bit simpler to read and keep it down to a number of lines. Here is the data that we actually want to protect. Rather funny size piece of data. That means we'll have to round that up when we actually want to protect particular pages of memory. Here we actually have the 2 keys that we're going to use, and then here we have 2 functions which are going to read and write our data, and we'll use our keys to control these whether they work or not. So this would be the user written code, for example, in perhaps a database stored procedure. Now when we have a problem with memory protection, then we're going to call a signal handler, and in this case the signal handler just simply prints out which signal it got, and then it will stop the program. If we now look at our main program, we'll follow the logic of the code. The first thing we have to do is called key enable. This switches on our user key access, and it returns the number of keys, so we'll just print that out. The next thing we have to do is to work out what sort of page size we will return when we actually allocate memory. We're going to use the vmGetInfo system call to do that, and it will tell us how big our memory pages are. Then we're going to take our memory and use the roundup macro here to round it up to the number of pages we need. And then we're going to call this POSIX mem align, which is like a malloc call, but will give us the block of data on a memory boundary, which we need to then actually set our locks against. In phase 2 then we're actually going to just write to the memory just to prove we can do it. Then we're going to protect this memory. Here's the call. We're going to give it the pointer to it and this size of the memory that we want protected. Once we've done that, we can then work through our keys. Let's scroll down a bit. Okay, so we have it protected. Let's go and create some keys so we can get into that memory. We'll initialize this reader key, and then we'll add to that the read permission to it. We actually copy the reader here to the writer, and then we also add the read-write permission to the writer key. Finally, that's just created our keys. To get that key in our hands so we can open a lock, we use the activate, and we're going to activate the writer key to start with. Then down the bottom we're actually going to run our tests accessing the memory. So we've got the writer key in here, so we've got the writer key and it should work to read it and it should work to write it. Then we're going to switch to activate the read-only key. So when we do that, we should be able to access it for reading, but when we try to access it for writing, that should fail, and we should find that as a call to our signal handler, and then it should stop. So let's just run that program now. So we can see here we get 2 memory keys, disappointingly low number of keys that we have access to as a user program. We find that it's just a regular program, so we've got 4K pages as you might expect. Data size is a bit over that, so we round that up to 2 data pages, and we can see here the address has got zeros in the bottom bits as it's page aligned. Then we can see we use the as the read-write key, the reads and writes should work. Then we went to read only, and the read should work and the write should fail, and we got a core dump. Now if we look with a debugger at the program and the core file, that tells us that where we actually failed and why we failed, segment violation, and on line 25. And if we VI that program, line 25, there we have that line in the writer that caused the memory violation. So now as a programmer we can go and fix that in our code. Now there's another option we got where we could actually use long jump and set jump to recover from these problems, and that's what we do in this other version of the code. It's a bit longer, so we won't go through the code, but again we find much the same algorithm here. 2 memory keys, we've had to increase the size of the memory. Then we've did a read and writer, that should work. Then we did a read only, the read worked, the write failed. We ended up in the signal handler here, but we actually running now in our signal handler. There are no access to the keys inside the signal handler, so we've changed to be the read-write key so that the signal handler here can actually access the data. And then it's asking us, do you want to do a long jump back to the main code and then avoid making this call to the function that caused us to fail. So yes, we'll do that. And we've gone back, we've recovered from our long jump into our main code, and then we're going to carry on working. Now we're doing a test for no access at all. So in this case the read should fail, and it did, and again we've got back to the signal handler. So you can get the idea that perhaps a database running a stored procedure or a user written piece of code can actually recover from the badly written piece of code and carry on running. This file has a number of things that you should be aware of before you start using these memory keys. If you're running the older AIX 5.2, this maintenance level, then you'll just get a return of no keys. If you're using an older version of AIX, then you'll find that the memory keys library is not available, so you can't start your program. If you're using AIX 5.3, maintenance level 6 or above, then you'll be returned with the number of keys available to you, but if you're not on a Power 6 machine, which is mandatory, then you'll get an error returned. If you're on older versions of AIX, you could put your key access functions into a loadable module and then decide whether to load that module at runtime. There is a very limited number of real keys on the system, and you're encouraged to use sort of virtual keys and move the real keys around when you recompile your program so that you can actually test various modules inside your code. You also have to decide what to do if you have a memory protection signal generated. You can catch it and find out where in that program it actually happens. You could then stop your program, but that's sort of disastrous for your users. You could let the program continue to run, hoping that we've got away with this for a long time, so maybe it will work this time. We'll go and fix the bug for real. Or you could decide that perhaps if it's a user function, like a stored procedure in a database, you could decide not to run that stored procedure until the user that they've got errors. And you can actually catch the signal and then do a set jump, long jump back into your program to work around the problem. The memory keys are ignored for CPUs that are reading program instructions from memory. That would be very difficult as it does read ahead of your instruction stream. As a warning that memory map files can't be protected, and you have to be very careful with your data and page alignment. And we've seen the worked examples of how to actually get that as a programmer. And finally, a comment on performance. The protect system call goes and puts all the locks on memory pages. Now, if we've got gigabytes of memory here that we're going to protect, then it will take some time, but of course we should only do that once when our program starts up. The activate is a simple system call, so that should be fairly quick. But you shouldn't be doing that thousands and thousands of times, only as you start a particular module perhaps, and then come back you'll reset the keys. And finally, signal handling, of course, that depends what you're doing in your signal handler, but one hopes that we're not calling signal handlers thousands and thousands of times. We should be removing these errors and eliminating them completely, so that shouldn't cause a performance issue. Well, that's it for memory protection keys. I would refer you to this particular website here. It's a library of AIX white papers, and there's one white paper called Storage Protection Keys that goes into this in a lot of detail. Although the white paper is quite complicated, and I had to read it 3 times even as a kernel programmer to understand it fully. If you want a copy of the source code that we looked at in this example, you'll find it at the website at the bottom.